The next experiment is decision tree. Every day on day-to-day basis, we make so many decisions but based on certain conditions, and uh, this is called a decision tree, where a graphical representation of all the possible solutions to a decision based on certain conditions. So, for a small data set here, manually when we have to draw a decision tree. So first we'll be taking the diameter uh, for as a root node, and for that diameter, what will be if my diameter is greater than or equal to 3? If it is true, what are the data that comes under that category? Or if it is false, what are the data that will come under the false category? So under the true category, it is the diameter is greater than or equal to 3. Mango, lemon, the labels mango, lemon, and other mango comes. And here, if you could see, when it is less than 3, there is only 2 data that are grapes. So it is 100% confirmed that if it is going to be false, it is going to be grapes. But if it is going to be true, then it can be either mango or lemon. So the next decision criteria is based on the color. So based on the color, if it is going to be not yellow, equal to yellow, then there is a chance of being the fruit being a mango or a lemon. And if it is not yellow, then the only option that we have is green, and it is going to be 100% mango. So this is how we construct a decision tree. So the manually we have constructed a decision tree, but for huge amount of data, so to train the system to generate a decision tree, we will look into how that works. So decision tree is a supervised learning algorithm. It uses tree-like model of decisions. It can be used both for classification and regression. That's why the decision trees algorithms are referred to as CART, classification and regression tree, where each node, for example, here the node sex, here the node age, here the node sibling. Each node is the predictor variable, or we also call it as features. And the link between these nodes represent a decision. And the final outcome or the target or the response variable is whether the labels are died or survived. So that will be the response or the outcome or the target. And in the decision tree, the first and the starting point of the tree is the root node, and this is the topmost level of the root will always take the topmost level, and this is where the split is performed, and it is the most significant node, because when the best selected node will help us to have the split very effectively and efficiently. And all the intermediary nodes are called internal nodes, and the final node or the final class that represents the decision are called as leaf nodes. And the algorithm for decision tree is how we have to select the first root, the best node as the root node, because that will be the best predictor which will separate our data into the classes most effectively and efficiently. That has to be the best split. And when we do the best split only, we will be able to get a proper classification. If we select a root node randomly, then we will not get an effective and accurate results. After we select the root node, we assign it as the best node as a root node, and then we start to build our intermediary nodes, and the leaf nodes are assigned, and if the data is correctly classified, we can stop. If it is not classified, then we have to reiterate the tree once more based on changing the decision of the root node or the predictor variables. How are we going to select the root node? The best node can be selected based on Gini index, or information gain. There are various ways where information gain is helpful here to select the best or the root node. There are various ways. One such way is ID3 algorithm, which uses the concept of information gain, where when we use information gain, we have to select or calculate the entropy. What is this entropy? Entropy is the measure of impurity in the data set. The uncertainty is measured. And when the information gain is high for any feature, then that can be accepted as a root node, because that predictor variable which is having the high information gain will divide the data into the proper desired output classes. And so we have to select information gain, which select a feature which is having a high information gain. That means that particular predictor variable has as much as information as possible that will reflect in the final outcome. And to measure the entropy, so when we measure the entropy of any data, when all the data, if it is for an example, if it is a two-class label where we have S and no as our classes, when all my data are of S or all my data are of no, either S or no, then it becomes, then it is a pure node, and we have for pure node, the value of entropy is 0. If my proportion of my data is half of my data is male S node, or half of the data is no class, then equally, if it is equally 50% proportion of male or S class and the no class, or male class or a female class, whatever it might be, then my entropy is 1. And there is a range of entropys from 0 to 1. How are we going to navigate through the problem? For an example, there is a small data set given where we have row type, obstruction, and speed limit as our features or predictor variable, and the speed is the target variable. So how are we going to classify or come up with a decision tree? So we have to now select the best variable. So the best variable is the one that splits the data set efficiently, and that will be considered as the root node. So to calculate the best variable, we have to find the entropy and the information gain. So this is our target or the class label, where we have 2 slow labels and the 2 fast labels. So this has 4 the 2 classes which are slow and fast, where we have 4 labels. And this is considered as a parent node, and we are going to calculate the entropy of the speed. So this is the target variable. So when we calculate the entropy formula is here for any subset of, for example, now the subset is my speed from my data set. For any subset of my data set, then minus sum of I till C pi log to pi. That means this is the proportion of the ith class, and C is the class labels in my subset. So now, for out of my 4 data, there are 2 classes. One is slow class and my fast class. So proportion of the slow class will be 2 by 4, and proportion of the probability of the fast class will be 2 by 4. So now I have got 2 by 4 for slow and for fast, so it is 0.5. So when we calculate the entropy is calculated as minus, so for the slow class. So proportion of the slow class log of slow plus proportion of the fast, the same formula is applied here. And when applying the values, we get the value as 1. So now while looking at this, also we can assume or know the entropy 2 out of my 4, 2 equally proportioned. My classes equally split. So like 2 slow class and 2 fast labels in my 2 classes. So it can be 1, as we have already seen. And we have to calculate the information gain for the child node. So so each row type is one feature, obstruction is one feature, and the speed limit. These are all considered to be the child nodes, and we are going to find out the information gain for all these 3. So for the row type, we have steep and the flat class. So for the child row type, when it is steep, the labels are 2 slow and 1 fast. The labels are off. And for the flat, it is of 1 label fast. So entropy of this fast is 0 because we have only one label, and it is 0. That means it is pure. But if you could see here, we have two slow class and the other label is fast. So for this, we have to find the entropy of the left child for the left node. So the left child of the node is out of 3, 2 for the proportion of slow is equal to 2 by 3 and the value is 0.6. And for fast, it is 1 by 3 and it is 0.33. So when we consider the entropy of the child when the row type is steep, then the entropy value is 0.9, and for flat, it is 0. So now we have to calculate the information gain, entropy of the parent. We have already found out the entropy of a parent here as 1. So entropy of the parent minus the weighted average of the each children. Okay, entropy of the children. So this entropy of the child node, now entropy of the row type is my child. So we know the parent is 4, the right child is 1 here, and the left child is 3. Okay, so now to calculate the weighted average for the child row type is the left child by the number of parent when the row type is steep, and the number of right child by the number of parent when the row type is flat. So when the row type is steep and for the row type is flat, we are calculating the weighted average of both left child and the right child for the row type child. And the same way we have to calculate for the obstruction. And when we calculate for the obstruction also, here we have equal partition. So entropy is 1 for both yes and no. And to calculate the weighted average, we are calculating for the left child when the obstruction is S, entropy of obstruction is S, and the right child into the obstruction is no when the obstruction is no. So now we get the value as 1. So we have found out the weighted average for the road type, child obstruction, and the same way we have to find it for the speed limit. And once for the speed limit also is found, then we have to calculate the information gain. Now, how is that? We are going to calculate the information gain. The predictor or the variable which is having the highest information gain is considered to be the root node. So now we'll calculate the road type for the information gain for road type. So this is the target 1 minus for the road type is 0.675, what we have calculated, and the answer is 0.325. The same way for obstruction and for speed limit. So from this, we come to know that speed limit, the child or the predictor variable of the speed limit has the highest gain. So we'll use speed limit as the root node. And when we split the speed limit as root node, it has two S and a child as S and no, and which have for the S, it is slow label, and for no, it is fast class. So it is equally split and there is no need for a further split. And so now the best variable is speed limit, which is selected as a root node, and we have developed or generated a decision tree. And based on this, the Python code for decision tree, as you all know, the data set is loaded, and in the data set, we have to load all the performance metrics that we are going to measure: confusion matrix, accuracy, recall, precision, ROC curve, and AUC curve. And these decision tree, this is the decision tree classifier, which will help us to generate the model. And after we generate the model, after we import all the variables, we have to now select our which will be our independent variable and which will be our target variable. So to calculate the independent variable, we are going to take features from 4 to 13. From the 4th column to the 13th column, all the rows. So these are the 4 from BP, cholesterol, and all these things we have taken, and the target variable or the dependent variable will be the 14th row. 14th column, and which has S and no values in that. And this Y target variable we are assigning label encoder, which will help us to convert our categorical data into the numerical data, which machine can understand. And we are once the conversion is done, it is analyzed and fed into the system for further processing. And now we have to split and train our data. So when we are taking the X and Y, the dependent variable and the independent variable, and we make sure that 80% training data and 20% testing data is we split it 80-20 ratio, and then my training data is given for decision tree model. Now we have the decision tree classifier, and we generate the model using our training data. Once the training data is system is trained with our training data, we will do the predicting of the results. So we can predict using decision_tree.predict, where we give the testing data. So when we give the testing data, we will be able to predict the values, and based on the predicted values, the tested value and the predicted value, we will check for the confusion matrix. If you could see here, the confusion matrix is 23 and 23, 6, 11, and 21, where there are 23 correctly predicted values of S and nearly 6 incorrect prediction of S. Actually, it should have been no, that means 0. It should have been 0, but it was predicted as 1. And here, if you could see 11, and this is false negative. So it is incorrectly predicting no. And the model, correct here, if you could see 21, the model is correctly predicting as no. So that is the true negative. So this confusion matrix is generated the same way. The accuracy, recall, specificity, precision, F-score are all calculated. And the ROC curve and the AUC curve is also generated. The ROC curve is called the receiver operating curve, where it is a graphical representation of the binary classification model. It is helping us to represent or plot the true positive rate and the false positive rate. Versus the false positive rate, it is helpful for us to classify differentiate the classification threshold. And this AUC curve, the value, if you get the high AUC value, then the model is better model, the good model. And this AUC curve helps us to measure the overall performance of our binary classification model, any model. Okay, so that's all. If you could see, the training data is given to the decision tree classifier to generate the decision tree, and the decision tree is generated. Okay, so this is with respect to the decision tree.